I'm also finishing my PhD, so I'm a PhD candidate at the University of Arizona.
And hi, my name is Adam Catlin. I'm a project scientist with GeoSyntec as well. I have about 12 years of experience, primarily in Nevada, and I've been with GeoSyntec for almost 3 years now. Primarily due diligence, subsurface soil and groundwater investigations, and groundwater remediation. So mostly I've done petroleum and chlorinated solvents, but now with GeoSyntec, big focus for us is PFAS, which is what Matt and myself will be presenting on right now.
All right. With that, I'll take it away. I'm going to cover the first part of this presentation, which is going to focus primarily on the fate and transport of PFAS through the vadosome. The goal of this first part of our presentation is to just build a general background of PFAS retention mechanisms in the vadosome. And then we want to kind of couple these retention mechanisms with larger scale fluid flow processes in the vadosome. So by the end of this, you should be able to understand what systems retain PFAS in the vadosome and then how PFAS actually move through the vadosome. And with that, I'll get going. So just wanted to start with a basic background on PFAS. You can see over here to the right, we have a PFOS, the molecular structure of PFOS. And this PFOS has a head group and a tail group. And most of the PFAS that we encounter and all of the PFAS of concern, which are listed here, all contain this specific head group and a tail group. For our PFOS, PFH excess, anything with the last letter S in it, we're going to have sulfonates. Anything with the last letter A, we're going to be carboxylate. So this head group is either carboxylate or sulfonate. And what's important about that is that these are all acids, right? And so I have the pKa's of each of the PFAS compounds that we're concerned about over here to the right. And if you don't know what pKa is, in its simplest form, pKa denotes at what pH the PFAS molecule will be protonated. So above a pKa for like a pH of 7, our PFAS of concern are deprotonated. So they all maintain this negative charge. And that's what is important because all of our PFAS that we're concerned about are negatively charged, and that creates this hydrophilic head group. The other portion of the PFAS molecule, this tail that's denoted, is composed of fluorines, which are the green circles, and carbons, which are the black or the gray. And this is what we call a fluorocarbon tail. And so this is very similar to a hydrocarbon tail, except for all the hydrogens in our hydrocarbon are just replaced with fluorines. And this creates a hydrophobic tail, but by replacing all these hydrogens with fluorines, we also create this lipophobic property, so it doesn't dissolve well in oils either. And that creates the unique property that PFAS gives that makes it really good for all sorts of things, including AFFF application, use in these firefighter foams. So now that we know the general properties of these PFAS molecules, what does this mean for our PFAS transport in the vadosome? And so first and foremost, our PFAS are dissolved in the pore water, right? So because of that charged head group, our PFAS are generally dissolved in the pore water. Also partially because of this, but also just because of the molecular structure itself, these PFAS do not necessarily partition into the gaseous phase. They're not volatile, so they're not like our TCE. They don't necessarily partition into this gas phase. And so our PFAS transport, it's largely driven by our pore water-based processes. This includes the advective transport, just fluid flow or infiltration or water moving through our vadosome. But we also get some diffusive transport that's driven by concentration gradients. And we think of something such as an aqueous film forming foam being applied to the surface. Those are applied in really high concentrations. So we can get this diffusive transport, but also due to our infiltration, our advective transport is what drives this PFAS fluid flow through the vadosome. In these soils and in this unsaturated system, the PFAS is largely retained by our soil water interface and our air water interface. And so these are primary regions of retention in the vadosome. And so I'm going to dive a little deeper coming up into what drives the soil water interfacial retention and the air water interfacial retention. So starting with our soil water or solid phase retention, our soil PFAS is largely retained by two mechanisms, right? Again, breaking it down by this head group and the tail group. So we have these head group driven retention mechanisms, which are surface reactions and our electrostatic interactions. And then we have our tail group mechanisms, which are our hydrophobic interactions. And I'm going to dive even further deeper into these coming up. So starting with our head group mechanisms. So our head group mechanisms, as I've previously talked about, is just broken up into these chemical reactions and electrostatic interactions. We know that PFAS is generally negatively charged at our conditions that we see in the field, in the Veda zone. And our soil is generally negatively charged as well. So we actually have a lot of repulsion of our PFAS head groups and our soils. However, we do have some positive charges contributed by metal oxides and other constituents. And so these positive charges create an electric field that causes an attraction for these PFAS. And these electric interactions are largely long range, and so they're denoted as outer sphere processes, right? So the PFAS are largely tamed farther away from the solid surface, whereas these chemical reactions, these inner sphere processes, such as ligand exchange, so a physical chemical interaction or reaction with the surface, is going to be much closer and hold these PFAS much closer to the surface. So we have these two processes, but what's really important about this form of solid phase retention is that it's not really different across all the PFAS, right? We have largely the same head groups. And so these head groups, if they're what's driving the retention, then we're not going to see really any difference between all of our different PFAS species driven by this head group interaction. So that takes us to our tail group driven mechanisms. And what these are essentially just hydrophobic interactions. And at its base level, these hydrophobic interactions is the minimization of the area of contact between our water and our nonpolar molecules. That is you see the water molecules that surround this PFOS molecule. We want to minimize the number of those. And so one of the ways we can minimize the number of these water interactions around this PFOS molecule is by driving it to these surfaces, specifically uncharged organic and uncharged mineral surfaces. And so this hydrophobic interaction really pushes these PFAS to these solid surfaces. You could also imagine that if we were to change the size of this molecule, specifically the molar volume of this molecule, like if we were to cut off 4 of these PFAS or 3 of these PFAS and end up with a smaller molecule, we would have lower numbers of water interactions around this molecule. And so by changing the molar volume of our PFAS, we're really changing the magnitude of these hydrophobic interactions. And so you can imagine, and I'll talk further about what this means for our PFAS fate and transport, as well as potential characteristics we see in the soil. Just for reference, these hydrophobic interactions are often represented by the standard notation KD equals KOC FOC, where our solid phase absorption, KD, is a function of our organic content absorption coefficient and our fraction organic carbon coefficient, because this is largely where our PFAS are driven with these hydrophobic interactions. So diving further deep into this, right, I want to start off by giving a visual approximation of the molar volume PFOS, right? And so you can see if we expand all those molecules or those atoms out to their van der Waals spheres, you kind of get a feeling of what these PFAS molecules look like with molar volume. And basic definition of this molar volume is just the volume of space occupied by the substance, right? So it's, how much volume does this or a mole of this occupy? So we calculate that in centimeters cubed per mole, right? So that the volume centimeters cubed per a single mole of these molecules. And we can do that for all of the PFAS, right? So we can do that for PFOS, we can do that for PFHXS, we can do that for every single PFAS. And we get this relationship, right, where these PFAS, these short chain PFAS have a lower molar volume, and they also have a lower retention in the system. Whereas our long chain PFAS have a higher molar volume, so around 350 and 300, and they have a lot higher retention in a lot of our soil systems. This is denoted by our KOC in this case. And so we see that this change in our molar volume drives this differential absorption of our PFAS species. So I want to stick on this plot for just a little while longer because I think it's really telling as to how PFAS move specifically through the vadose and through our soils, because we have this really interesting break where we have a log linear relationship right here for our quote unquote long chain PFAS. And then we have a significant deviation from that log linear relationship for our short chain PFAS. And that's because our long chain PFAS, our PFHXS, our PFOA, our PFNA, and our PFOS are largely driven by these hydrophobic interactions, right? So they have enough significant molar volume that the main driving force for solid phase retention of these PFAS is this molar volume, this reduction of our interactions with water. Whereas our short chain PFAS, you see here, largely deviate from that log linear relationship. And that's because those ones are so small that these hydrophobic interactions do not dominate our solid phase retention of these PFAS. In fact, most of these are driven by our head group mechanisms. And if you remember when I was talking about that, I was saying how this is not really, they don't really change and are not really dependent upon the PFAS molecule or the molar volume. So you can see like a lot of these, once you get to a certain point where these hydrophobic interactions aren't controlling the absorption of these PFAS, namely the deviation from this log linear relationship, we have a flattening out. And that's because, again, there's not any significant difference when you're driving these PFAS to the soils based on this head group mechanism. Moving on to air-water interfacial absorption. And I just want to state that PFAS will accumulate at the air-water interface. As you can see here in this graphic, there are different points at which the PFAS can accumulate, right? So you can accumulate in this capillary retained water, but also in this thin film retained water. And so there's important points to say that there's a lot of air-water interfacial area in the system, and PFAS will accumulate at these air-water interfaces. And again, these are largely driven by the hydrophobic interactions. And so we'll see the same very similar log linear differential absorption based on molar volume. So looking at this plot over here, if we take our solid phase absorption and plot it alongside our air-water interfacial absorption, we get a very similar log linear behavior. Namely, and that's pretty indicative of the fact that what drives this retention is a similar hydrophobic processes. A significant difference between our solid phase absorption and our air-water interfacial absorption is that our air-water interfacial absorption our air-water interfacial absorption coefficient, KAW, in this case, is much, much lower than our solid phase absorption. However, our air-water interfacial area is, our air-water interfacial retention is also driven by our magnitude of air-water interfacial area. And so at low saturations, we have really high air-water interfacial area. And so at some saturations, this air-water interfacial retention can be the most significant retention mechanism of these PFAS in the soils. So I just want to talk a little bit more about what air-water interfacial area is and the magnitude and its relationship with water saturation. So if you look at this graph over here to the right, you can see that there is still some area, the air-water interfacial area is still a space where we're trying to figure out what is going on, and it is an area of ongoing research. What I want you to take away from this is that the magnitude of air-water interfacial area is much higher, is much more significant at low water saturations. So at the low water saturations you see in arid regions is often an important player in this PFAS retention. But if we move to higher saturations, right, we're not going to see as much of this air-water interfacial retention, and because this air-water interfacial retention is much more lower, it's not as strong as a retention mechanism as our solid phase absorption, we see at our higher saturations, it does not play as significant of a role. So putting it all together, I just want to talk about what this means for our PFAS in our soil. So I've talked about this differential retention of PFAS, and you can see here, I kind of depicted this in a little GIF. And so we have our lower molar volume PFAS in orange and our higher molar volume PFAS in yellow. And you can see that our lower molar volume PFAS aren't retained as much, right? And so if we apply a mixture of the two, the orange and the yellow up at the top, our orange is going to break through much quicker than our yellow. And that's because our higher molar volume species are retained at the soil water interface, at the air water interfaces. And so they move much slower than our lower molar volume species. But say we apply this PFAS as a mixture of different PFAS, we're actually going to see significant separation of these species in our soil systems, as our lower molar volume species are less move with the effective domain of the water, and our high molar volume species are retained and move much slower. So if we look at this figure here to the right, you can, if we imagine this graph output, right, our orange is moving faster, and so we see an increase in the population of this orange lower molar volume species before our yellow higher molar volume species. So generally, just to give a brief overview, our PFAS are dissolved in our vadosome pore water, and they move with the pore water. Again, this is a really important concept, primarily, especially here in the arid Southwest, in Nevada and Arizona. We have to really think about where the water is moving, and I'll move forward and talk about that shortly. But also, our PFAS is retained at our air water and our soil water interfaces. And so these processes are largely driven by hydrophobic interactions, and those are a function of our molar volume. So as our molar volume changes between these PFAS molecules, we see this significant chromatographic separation. And then lastly, our air water interfacial area is dependent on our water saturation. So you already see this link up between our larger fluid flow processes in our system, as well as our retention of our PFAS in the system. So I'm just going to move on and talk about general fluid flow processes in vadosome and its interaction with PFAS. So starting at the surface soil, right, we have a higher organic carbon in the surface soil. So we'd expect to see a higher retention of PFAS by the soil, and we generally do. We also see higher variations in water saturation, right? So you can imagine we have a large rainfall event, we're going to have high saturations near the surface, and then we have really sunny, hot days that follow it, like we do in Tucson. And we'll see the soil dry out really quickly near the surface. And so we have these wild fluctuations in our saturation. But we also have added absorption to the soil phase because of this higher organic carbon. And so this drives really complex and interesting and difficult to really understand transport mechanisms through the surface soil. Moving deeper in the vadosome, this high fluctuations of water tend to stabilize out more, so we get much more stable water saturations. But what we see deeper in the vadosome is the impacts of these larger scale properties, right? So physical heterogeneity, where we have different inclusions of clays or sands or silts, and what that does is it actually provides pathways for transport of PFAS. So preferential flow through the vadosome is an important characteristic to try to understand how PFAS move through this vadosome. Secondly is these climactic impacts, right? So how much is it raining? What is their infiltration or evapotranspiration, right? So again, I'm based in Tucson, and I see something called a calcic horizon that's often, represents the maximum infiltration essentially of our water in our system after rainfall events. So we have our infiltration, but then we have so much evapotranspiration that the water actually doesn't really infiltrate all the way to groundwater. Instead, it evaporates out. And so what we're left with is this barrier or this layer that demonstrates, like, essentially that has this buildup of all this other stuff that is our calcic horizon. Lastly, the capillary fringe. It's a region of capillary retained water, which is linked to groundwater, right? So we have our groundwater fully saturated. We have an unsaturated region above it that is directly related to the groundwater below it. So it's linked to the water, but it's also unsaturated. And sometimes when this groundwater is up high enough, we can actually link our groundwater to our surface through this capillary fringe. So putting it all together, I just want to go through a case study that demonstrates the interrelationship of these fluid flow aspects with our solid phase and air water and our retention aspects of our PFAS. And so this is based on a case study. an upcoming paper called High Resolution Depth Discrete Analysis of PFAS Distribution and Leaching for a Beta Zone Source at an AFFF impacted site. Essentially, this was an AFFF impacted site. So they sprayed a bunch of aqueous film forming foam all over here because they were doing fire trainings. And they sprayed it for 20 plus years on an online fire training areas. And it's been 50 plus years since that first application. The site is a semi-arid environment. So again, we see this high evapotranspiration and low infiltration. So what did we do? What we did was we assessed the PFAS concentration in 3 separate cores that spanned the entire beta zone, so over 300 feet, because the depth to groundwater in the Tucson area is significantly, is really deep. And because of this depth, we approached it using a telescoping approach, right? So we started with a relatively low resolution analysis that gave us generally where our PFAS was, and then we zeroed in to where the PFAS was for a more high resolution core. And once we figured out that the PFAS was confined near the surface, we actually extracted 1.5 meter cores, as you can see here, and segmented them every 7 centimeters. So what we did once we segmented them is we performed a PFAS analysis for 48 different PFAS compounds, but we also performed a soil analysis to determine what soil characteristics are important in understanding this PFAS movement through the beta zone and what it can tell us about the PFAS movement through this beta zone. So what we first learned is that 99% of the PFAS was contained above 3 meters, which is given here. So because of the large depth, we had to provide it in a log access. But you can see that we have a significant increase in our PFAS concentration, coincident with this 1 meter mark. And that's actually coincident with the onset of this calcic horizon. Below this, we have below 10 meters. So below this, we actually didn't see any PFAS. So we have all of our PFAS primarily is contained within this upper 10 meters of our soil, which is really interesting. Then we characterize the soil. And this is a few of the characterizations presented. I just picked these out just because I thought they're relevant, but we did a lot of other characterizations. One I think is really important is our carbon. So if we look at our organic carbon, we don't really have a lot of organic carbon. So we're not having a lot of retention due to organic carbon. What we do have is a lot of inorganic carbon down lower alongside this onset of our calcic horizon. You can see it in this area here. It's lighter in color than the surface soil above it. And so this inorganic carbon you can see is almost coincident with that increase in PFAS concentration. We also see an increase in our metal oxides in this layer, as again, these are our metal oxides infiltrate down with our rainwater and they build up in this calcic horizon. And we've talked about these metal oxides previously as an area of large solid phase absorption for our PFAS. So these are some interesting soil characteristics. Moving on to our PFAS distribution in the core. And again, this is from 0 to 1.5 meters or 160 centimeters roughly. So all of our PFAS, most of our PFAS was confined to these upper 1.5 meters, as you can see. But what's interesting is that if we break this down based on molar volume, our really high molar volume PFAS, our PFDOS, that you can see here is really a really large molecule, is confined to the surface of our soil core. So in 50 plus years of transport, right, this PFDOS is really not moved from the surface of our system. Whereas something smaller like our PFNS that has a smaller molar volume is moved throughout the core and is distributed broadly, but has a center of mass around 80 centimeters below ground. So it's moved, but not nearly as much as this PFPES, which again likely represents more of the advective domain of this PFAS mixture, or the advective domain of our soil system. And so that one's been transported really much significantly further down the soil core compared to these other two. And you can see that this molar volume is really driving, is much lower than a lot the molar volume of these other constituents. I also just wanted to note the center of mass. You can find these for each of these each of these PFAS distributions just using standard statistical analyses. And if we do that for all of the PFAS in the core, we can actually get a relationship of all of our PFAS with respect to molar volume. And this is a really interesting graph because it tells a really cool story, right? So you can see all of our high molar volume PFAS that are largely retained at the surface, right? So little to no leaching in 50 years. And we have our low molar volume PFAS, which are all built up in this calcic horizon right here at 140 centimeters below ground. And then we have this really interesting differential absorption of our moderate molar volume species, which are separated due to this differential absorption to the air-water interface as well as soil-water interface. And so we have significant chromatographic separation of all of our species, but they each behave relative to some of their molar volume properties. And so you see this broad distribution, and even our PFSAs and our PFCAs, they kind of collapse on the same sigmoidal function, where our molar volume is largely what is driving this different sorption of our PFAS species. So just to wrap it all up, what I want you to take away from this is that PFAS transport in the vadosome is both a combination of our fluid flow and our retention. So as an example, at this AFFF application area, our PFAS was retained in the upper 3 meters of soil due to our large-scale fluid flow processes, right? This is our evapotranspiration as well as our infiltration. That's what's confining most of this PFAS within the top 3 meters of our soil. And then even within these top 3 meters of our soil, we see large distributions and differential distributions of the PFAS based on their molar volume. And so this differential adsorption leads to this chromatographic separation of our PFAS, where our low molar volume species are largely reflect the effective domain, and they're dominated by these head group associated solid phase retention mechanisms. Our high molar volume PFAS are largely retained by soil and immobile due to the hydrophobic interactions. And then due to variability in our hydrophobic interactions in these moderate molar volume PFAS, we have a broad distribution of these PFAS species throughout the soil. And on that, I'm going to hand it off to Adam.
Thank you, Matt. Yeah, as Matt gave a good summary on how the fate and transport works in the subsurface, I'm going to kind of give a basic introduction to site investigation fieldwork planning. So give you an idea for sources where we would find PFAS historically or initiate a response effort, and also supply some planning strategies and tips that will contribute to successful field sampling programs. The next slide. So obviously I'm not going to go through this whole list, but PFAS in general has been found in a very wide variety of products, wide variety of manufacturers, and wide variety of uses throughout our everyday use and facility uses. I just wanted to highlight in green a couple of the everyday or sampling products that we use or would be expected to use at sampling programs that we have to be aware of that may contain PFAS, so that looking to limit our exposure to those. And also you'll see the first bullet that Matt mentioned a little bit earlier for the aqueous film forming foams, the AFFF. These are primarily going to be at airport, fire training facilities, or military applications, and are a pretty large source that we found for PFAS contamination in general. Next slide. So to begin with, when we're trying to find source area identification, there is some challenges that we have compared to what primarily consultants or anybody regulators would be looking for in determining past usage. The reason for this is because areas of current or former use aren't obvious. As we mentioned, if there's a fire training facility, that can be obvious, but a lot of the airport or military uses are, if you have a fire for a plane, that isn't going to always be in the same area. It's going to be in a kind of remote area out there that you need to get to. And so there's not going to be, it's going to be over a very short time frame that this response action is occurring. And so you'll have these situations where they'll respond, and then after that, once the fire's out, everybody calls it good and they move on. Also, because it was historically handled as an inert substance, if it was applied to, a fire training facility or planes or anything like that had a fire, then there was no response to try and clean up afterwards. Basically, it was the hazard is done for the fire, and then they would move on. Also, compared to what we would usually find like a phase 1 or anything like that, there aren't the telltale signs that we would look for on, say, a petroleum site where you would have a vent pipe or a fill pipe for a UST or dispenser islands, anything like that. It's all going to basically be historic things that happen and were taken care of, and kind of out of sight, out of mind things. So going along with that, it's very important to do site interviews and have knowledgeable contacts that can actually tell you what was done at a site and where some of these response actions might have taken place in the past, to try and see where you'd want to assess throughout a site. Next slide. So obviously, planning communication are always important. Usually when we are going out to do these field assessment events, we are going to be working with subcontractors and vendors to get the equipment that we need. It's very important to ensure that all parties are aware that it is a PFAS project. Luckily, because historically this is a kind of a emerging contaminant. So whereas before there wouldn't have been a lot of standard operating procedures out there or anything like that, at least now there has been a lot more research that's ongoing, and there's a lot of state agencies out there that have created these SOPs to aid in compliance and sampling. There's a lot of drillers that have specific SOPs out there, so that when they get to the site, they're ready. Obviously, we don't want to get into a situation where you just say, hey, I have a drilling project, and you send somebody out here and then come to find out that the equipment that they might be using is not going to be compliant for what we're trying to do out at a site. And then finally, for vendors, again, historically, it was a big research project where you had to try and work with people, work with vendors to see if they had products that were PFAS free. They might not have known. Now, a lot of vendors do have different versions of the same product that they can certify as PFAS free to help you out. Things like with pumps, you can have the same pump that you are used to at petroleum sites. And for example, they'll have a PFAS-free version of that, where it's just a bladder, for instance, that's PFAS-free, or for instance, hydrosleeves where they'll use HDPE instead of LDPE out at the site. So there are options available now for that, but you just have to do a little bit of research on the front end, basically. Next slide. So obviously, when we're doing field sampling, PPE equipment and supplies are something that we're going to need for every field sampling event. Just some items to avoid. The number one is obviously materials with fluoro in the name or Teflon. These are PFAS containing components, so we want to avoid that. It's not a big concern for most of Nevada, but water or stain resistant boots and clothing, because they may contain PFAS as their water repellent. Various cosmetics, moisturizers, and sunscreen is a big one, obviously, for Nevada for the work that we do, may contain PFAS, so you'll want to be aware of that. And then just from testing on food wrappers and packaging, some of those may contain PFAS. So again, just want to limit use of that. Next slide. And then there is still plenty of PPE and equipment that is safe to use that we would normally use, but you're just going to want to make sure for things that are safe to use, it will be high density polyethylene, silicone, acetate, and stainless steel are still okay to use. LDPE materials that aren't contact with the sample, this would be things such as trash bags, this would be Ziploc bags that aren't actually touching the sample, are still fine to use for field sampling programs. Again, there are rain gear out there that will have PVC or vinyl or rubber that can be used. And there is specific sunscreen that has been tested, as well as insect repellent that is PFAS free and can be used out there. And then normal PPE such as safety glasses, disposable nitrile gloves, and hard hats are all fine. The only thing to note with the fluorescent clothing is for the high visibility vests. You have to be careful with some of the reflective tape on those, which can contain PFAS. So I know for our field sampling events, at least we just do the cotton shirts that are yellow or orange for what we use in that regard. So next slide. Again, this is just a quick little safe to use versus things to avoid when you're out in the field for comparison. For safe to use, we have HDB containers and screw caps. You will want to try to avoid the glass sample containers because PFAS may adhere to the glass surfaces. If you're working with the laboratories, they will have all of the supplies that you need out there. But again, just communication to make sure they know it's for PFAS. You can use sample preservatives, Trisma. That will only be though for drinking water methods, as I'll explain later. Other things to avoid are Sharpie markers. So it'll have to be just pens that we use out in the field. And you want to avoid water resistant paper. A common one is the Right in the Rain products, which can contain PFAS, as well as plastic clipboards. And finally, you're going to want to be careful about aluminum foil and the Decon 90, which also may contain PFAS. Next slide. So in terms of types of media, it's going to obviously depend on the interviews that you do and the history that you get, but PFAS typically occurs in the following media and may be assessed based on initial research. That will include soil, groundwater, sediment, stormwater, and surface water as potential sources of PFAS. Next slide. One of the important things based on the prevalence of PFAS in the subsurface is to think about ahead of time where you're going to get your decontamination water from. Because we're dealing with parts per trillion on the results on this, it's very important to do a good decontamination program, and water is part of that. The first option that you have available is lab provided PFAS-free water that they will actually certify as PFAS-free. These will usually come in the gallon up to like 2 or 3 gallon cubes that you can get from the lab that they'll ship to you. These are often pretty expensive though, and in terms of the volume you're going to get, it can add up very quickly. So that's usually more of just what we'll use for blank samples and for a final rinse on the equipment. So therefore, you're still going to need probably a larger volume of decontamination water. Typically, it would be beneficial to try and get it from an on-site source, such as a hydrant or the public system tap. Before you go this route, though, we'd recommend ongoing testing of the source because water systems in the United States have been found to have PFAS in it. So you don't want to use a source that could possibly cross-contaminate your equipment or your samples right off the bat. If you are using a driller's tank for like soil sampling or things like that, we'd recommend testing of the driller's tanks or hose because it's not going to be clear if they're coming from another site where their water was from or any potential contamination sources that would be available in that. So we would recommend an ongoing testing to make sure that your decon water is good. If your testing does show or you don't have, or you're at a remote site where you do have to get off-site source of decontamination water, again, we're going to recommend the same testing to be done, but there's going to be a significant source of cost just for the transportation generally on that. So on-site is obviously the best, but we're just going to want to make sure that the testing has been done and that it's not a source of contamination for you. So in terms of the actual field work for groundwater, stormwater, and surface water sampling, as we said, there is a lot of products out there that are certified as PFAS-free. The actual procedures are pretty similar to what most consultants or regulatory agencies would use out there. The only thing is that there's generally going to be some added effort for the decontamination. Typically for PFAS, we'd recommend single-use or dedicated well sampling equipment to prevent cross-contamination and also to cut down on that decontamination time a little bit. Along with this, you're going to want to ensure that materials are compatible for PFAS sampling. No LDPE used out there. As I said, typically the most vendors will have HDPE options, but just have to ask. And also a lot of sites that we've come across have existing dedicated sampling items such as tubing or pumps in the wells. This is similar to the driller tank where we just don't know the procedures that were used in the past. So we'd recommend not using the existing dedicated items in there. And finally, the recommendation is not to field filter water samples based on just the interaction of PFAS adherence to the filters themselves. Slide. In terms of laboratory analysis methods, the current approved EPA methods are EPA methods 533, 537.1, and 1633. There's also a couple of matrices specific analytes out there for certain PFAS compounds, but these are the main three. So they're the ones that I'm just going to focus on for this presentation. To note, only EPA method 537-0.1 specifies drinking water sample containers utilize polypropylene containers. All sample matrices are collected though in polypropylene or HDPE containers, including the caps and the lids. So just make sure you're not grabbing, a glass container with a Teflon ring from off your shelf. You're gonna want to make sure you have the right materials. And except for drinking water samples, samples are collected in unpreserved sample containers. I also wanted to include for 1633 is the newest method, but just to give a comparison of 537.1 versus 1633, method 537.1 was approved in 2018, and 13 labs are currently certified by NDEP, Nevada Division of Environmental Protection for PFAS analysis. Technically, the method is only for drinking water samples, but commercial labs have developed modified versions for other matrices. The modified methods are laboratory specific and not standardized, but the results are valid. And because they are modified, you'll have a varying number of analytes reported under that modified method. The newest one is method 1633, which was just approved in 2024. Because it is so recent, there is no labs currently certified by NDP for the method in Nevada, but that will likely change in the future. The method was produced because it is for not just drinking water, but it's for soil, wastewater, surface water, groundwater, and stormwater. It offers the benefit of being standardized and will include 40 PFAS analytes. Currently, due to the limited labs that are currently certified nationwide, there is under DoD right now, there is longer turnaround times and higher costs currently, but that may be reduced as additional labs come online with the certification for that. The only other note is that greater sample volume is necessary. It's actually double what it is for 537.1. Usually for groundwater, for instance, we're filling up 250 mil containers, whereas for 1633, it will be 500 mil containers. So that'll just, again, be for just shipping and the method that you choose to use for sampling, but just something wanted to note on that. Next slide. As I mentioned, there's no local Las Vegas labs. I also checked there's not Reno that are certified for either one of the methods, so they aren't analyzing for PFAS at this time. So there is a significant volume of PFAS samples that are being submitted to the select national laboratories. So there is a longer turnaround time just because there's less offers of the service out there. So just we're typically seeing about 15 days on the 537.1, but I've heard as long as 4 to 5 weeks on the 1633 for some other projects there. So there is a longer turnaround time than for your usual analysis like VOCs and things like that. Per methods 533 and 537.1, samples should be chilled to at or below 10 degrees Celsius during sample collection and should not exceed 10 degrees Celsius when received by the lab. This means that because pretty much all of these samples are going to have to be shipped out a significant distance, that you're going to need a lot of ice. Because of the potential, again, for cross-contamination at these parts per trillion level, we'd recommend fresh ice should be obtained to keep it below temperature, and also that it'd be double bagged within Ziploc bags to prevent any of leaking, getting to the samples and potentially contaminating. We also recommend not to use the blue ice packs at any point in the process, just because of cross-contamination concerns and not knowing where those blue ice packs have been previously. Next. Another note also for investigation-derived waste, IDW, is to plan ahead and contact waste disposal facilities to see if they will accept whatever IDW you are generating. We've seen some reports around the country of landfills and water treatment facilities beginning to refuse waste derived from PFAS sources. This has a lot to do with just the changing regulation out there with how any waste or any generated materials are being regulated. So people are kind of leery about taking those weights on into their facilities. In terms of Nevada, just to give a kind of where things are for Nevada PFAS regulation, Nevada Assembly Bill AB 97 was passed in 2021 and led to the creation of the NDP PFAS Working Group. The working group was a wide variety of stakeholders, from regulators, consultants, environmental groups that got together to kind of look at some other states' programs and figure out some recommendations that they were going to be working towards. For the current Nevada reporting requirements under the AB 97 bill, they are fairly limited at the moment. The only two are either a mandatory reporting of the discharge, use, or release of Class B firefighting foams, which is that AFFF containing PFAS. So that would be either an accidental release from a fire truck or anything like that, or even if there was an intentional use of it for a fire, all of those would have to be reported for any amount. There's no limit on it. As soon as there's any sort of release, it has to be reported. And then also there's mandatory reporting of any PFAS released to surface waters in any formula. There's been a lot recently on the federal PFAS regulation side. Two things we wanted to highlight was on April 10th, the EPA finalized the national primary drinking water regulations for 6 PFAS, for PFOA, PFOS, PFHX, GenX, PFNA, and then there's also this mixture that is of the various PFHX, PFNA, GenX, and PFBS down there. So that's going to be in the next couple of years as that's rolling out, and there is now an MCL for most of those. And then also on April 19th, EPA announced the designation of PFOA and PFOS as hazardous substances under CERCLA. This was just published in May in the Federal Registry, so the rule will actually go into effect on July 8th, 2024. Going back to that Nevada PFAS working group, it was specifically stated in there that if any PFAS analyte was listed under CERCLA, that would go into the reporting requirements that we stated before. So there is likely to be some changes to the Nevada reporting requirements coming up, but there's no announcement on that yet. So that is our presentation. Thank you all for listening to us today, and we wanted to open it up to any questions that you may have. See, I don't see anything in the chat that was written, so I guess does anybody have raised their hand and we can unmute you then?
Okay, I don't see anything in the chat in the queue. Oh, here we go.
And I see Derek has their hand up.
Yep.
Yeah, can you guys hear me?
Yes.
Do you guys know of any? It's obviously thank you for this presentation. It's really really helpful. Obviously sampling and the procedures and everything that go into it are going to be very very sensitive to this contamination. Do you guys know of any training in the works for like operators to attend to kind of learn how to do this sampling, or what what materials and the equipment to select to make sure we're not getting cross contamination, or is that still kind of in the works or unknown right now?
I would say it's unknown. I'm not aware of any, at least I should say, or that anything has been planned. Like I said, the NDP PFAS group put out their like final report in 2022. So there hasn't been, anything new since then. I think maybe with the CERCLA designation, there may be some new requirements coming out. So maybe something coming with that, but I'm not aware of anything official that's been put out there for that.
Okay, I appreciate it. Again, thank you for this presentation. It's been, it's a lot to take in for, I know, for a lot of agencies. So everything helps. So very much appreciated.
Of course, you're welcome. And then, see, is it Trina?
Yes, hi, can you hear me?
I can't.
Great. You mentioned that some landfills and wastewater facilities are not taking PFAS laden, soil or materials or water. What mitigation protocols, or are there any to remediation, I guess is the word, that can be done so that you can dispose of those types of things? I'm thinking contaminated construction sites, things like that.
You know that one? I know that EPA is also just within the last month kind of put out some interim technologies that they had out there. I know they had injection. I know there was thermal treatment. There's one more that I can't remember right now, but I don't know if that's something that would need to be completed before it gets to the disposal facility, or if that's something that the actual facility would do before they accept it.
Okay, thank you.
Okay, does anybody else have any questions? If you do think of something, or something comes up in the next couple of days, and you have some questions, if you want to just go ahead and send them to me at the same email address that you received the login instructions for this webinar for today, I can forward those to Matthew and to Adam, and maybe you can get them answered that way. So something might come up after this webinar, and feel free to still send it in. Thank you so much for joining us today, Adam, Matthew. Thank you so much for your information. It was a lot. I'm not gonna lie. I kind of got lost a little bit there, but I'm sure everybody else that was on here loved it and understood everything that you said. So thank you so much for sharing your time with us today. And everybody will receive a follow-up email from Chrissy, certificate of attendance and evaluation survey. If you could please return the evaluation survey, that would be really great. And if you have any questions, or again, if anything comes up after this call, just go ahead and give me a call or an email, and I will send that over to Adam and to Matthew. Thank you so very much, everybody, and have a really great day.
Great, thank you.
Thank you.
Thank you.
All right, how do you guys think it went?
I thought it went good.
Good, good, yeah. There are a lot of big words in there. Somebody walked in and said, "What's the webinar about?" And I'm like, I don't even know. But they're doing a really great job. Okay. All right. Well, if you guys ever want to do this again, let me know, would you? Yeah, it was really great that you committed to this, and thank you so much. And what is the lady's name that helped to organize this with you?
Bella.
Bella. Yeah. Do you work in the same office with her?
Yeah, she actually is. She worked here, and now she's actually remote. She's in the Atlanta area now, but she's still, she's still part of the Las Vegas office, but working from Georgia.
Oh, nice, nice. Okay, I'll have to make sure I send her a thank you again. Are you both in Las Vegas?
I'm in Tucson, so and there's a lot of coordination between Las Vegas and Tucson. So I've come up there and helped some. So I spend some time in Las Vegas.
Oh, okay, okay. Because I see there's a Las Vegas address on the bottom of your screen there too. So is that where you are, Adam? Is in Las Vegas?
Right. That's where I'm at.
My son is there. He's going to Krikorian School of Medicine.
Nice.
And I I just talked to him yesterday and I asked him, hey, how's the weather? Because it's kind of getting warmer here. And he's like, it's like 95. I came out of the hospital today and it was baking.
Yeah, no, I was glad. We had some field work that we were doing. And it just finished like the day before it started to get hot out here. I think our luck's running out. We had it pretty nice for May, but I think we're going to be typical Las Vegas pretty soon.
We have a student that just started with Fish and Wildlife Service, and she had a desk job where she was at before, and so now she's out in the field. I said, your timing is horrible.
Yeah,
Horrible. Like,
yeah,
seriously.
didn't plan that good.
Yeah, we're gonna get her one of those hats, with the flaps that comes down. We're gonna get a cooling band. We're gonna send that to her. Yeah.
Very smart.
It'll
yeah.
help.
Anything helps.
Yeah. All right. Well, do you guys have anything else? Do you have any questions or do you need anything from me?
I don't think so.
Okay.
Yeah.
Do you want me to send you a final registrant list so that you know who actually attended and maybe you can use it for, I don't know, some mailings or something?
Yeah, that'd be great.
Okay. All right. Chrissy will finish up with it and she'll send it over to me and then I will get it over to you. And then if you have anything that comes up in the future or you want to do this again, please let me know.
Awesome. Will do. Thanks for all your help.
Okay. Have a great day.
All right.
Yeah,
bye.
you too. All right, bye.
Bye-bye.